The traffic engineering, the word traffic engineering, according to me, it's a mandatory. It is not an optional. But in networking, we see it as an optional one. Why?
Mhm.
Only when you enable TE, your routing protocol is going to provide you a, a decent service. When we
Okay.
don't enable TE, then you don't get uh, uh, control over the traffic flow. The path selection by the routing protocol are not up to satisfactory. That's why we need TE, traffic engineering. So if the routing protocol itself will have this TE inbuilt, that will be much better. But unfortunately, we don't have inbuilt TE with routing protocols. So it is additionally enabled by us whenever we feel it is so important for us. Whenever
Okay.
we feel it is too important, we enable this. Because by default, the routing protocols don't have this enabled. What all
Okay.
it takes to enable traffic engineering? For this, you need a link state routing protocol. So you need ISIS or OSPF.
Okay.
No other routing protocol. Secondly, what we need for traffic engineering is the MPLS, so that the labels can be used while taking decision on path selection. Thirdly, we need a protocol called resource reservation protocol. Resource reservation protocol, RSVP.
Okay.
With these three, also MPLS for the control plane. Sorry, BGP if needed.
Mhm.
Again, it's not mandatory. Let's put BGP. So with the support of all these three,
Mhm.
we can have traffic engineering. So simple routing protocol OSPF cannot provide you traffic engineering without working with RSVP and MPLS.
Okay.
So there is a dependency. But today's advancement, like SD-WAN, has these things orchestrated.
Okay.
So we don't really enable RSVP or MPLS. They get just enabled like that when you go and punch some buttons, and the traffic engineering is provided. Now, what is very important for a traffic engineering? If someone needs to do traffic engineering, say for example, your city that you are living, if someone needs to provide a traffic engineering, see it's always congested, the roads are too congested always, the time taken to go from one place to another, it's taking more than what it's supposed to take, which means what? There is no traffic engineering. So now
Okay.
if you want to appoint someone as a person in charge of controlling the traffic, if you want to appoint someone as an officer who can control the traffic of that town or city that you are living in, what sort of person he should be? he should be a person who has got the complete visibility to the town or the city. If he is
Yeah.
just one North Indian coming to South Indian or South Indian going to North Indian, he cannot be a controller of the traffic because he do not know the city. He do not know the town. Who can really have the knowledge of providing good traffic engineering? The one who knows the streets of the city very well, the town or streets of the town very well. Only he can provide proper traffic engineering, the real good traffic engineering. With no knowledge about the city, if someone comes as an officer and say, I'm going to control the traffic, only in word it will be there, in media it will be there. In practical, it is not going to happen. That's
Yeah.
not going to happen because you don't have the visibility to the links that are connecting in between the streets. Likewise, if we need traffic engineering, MPLS is actually making the packet forwarding faster by using labels. It looks into the incoming frames, incoming packets label and decides the exit interface and the gateway towards the destination. On top of that, we need traffic engineering so that this MPLS needs a link state routing protocol. Link state routing protocol is like the officer who knows the town, the city very well. Link state routing protocol will have complete status of the link in the link state database, LSDB. So we must enable a link state routing protocol in order to have traffic engineering. You cannot have a distance vector protocol. Distance vector protocol is like an officer who says, I'll take care of the traffic very well. But he is no way from that city or from the town. He has just got transferred from another state to this state. How he is going to control? Nothing. He will simply listen to the other juniors and whatever they say he is going to follow. He cannot be a real creative traffic controlling officer because he is learning by rumor like RIP and EIGRP. So you need a link state routing protocol so that you will have complete visibility to the town. Likewise, when you need a link state routing protocol, you will have complete visibility to the topology. Only when you have complete visibility to the topology, you can take a very fine-tuned path selection. You can take a very fine-tuned path selection. You need the complete visibility to the topology. Now, the routing
Okay.
protocol that can provide you the complete visibility is only a link state routing protocol, isn't it? Only OSPF or ISIS
Yeah.
have got the
Yeah.
complete link state information. Fine.
Yeah.
Now, can OSPF and ISIS work with MPLS? Yes. ISIS and OSPF can work along with this traffic engineering protocol called RSVP, Resource Reservation Protocol, and MPLS. So it can work along with the OSPF and ISIS have got that knowledge to work along with RSVP and MPLS. In ISIS we used to call it as TLVs, type length value. Its type length value is nothing but the additional field, the extra field, right? It is so for traffic engineering, You need complete visibility to the topology, which is provided by IGP protocol, OSPF, and ISIS. There is no other protocol which will maintain the complete database of the topology. So you need a complete database of the topology. That's why you have to depend on any one of this protocol. No other protocol can be an option if you are doing traffic engineering. And then you need a protocol that will work along with MPLS and RSVP, because RSVP is the one which is going to reserve the resource for us. Means this is the one which is going to guarantee the path that has got good bandwidth, the sufficient bandwidth for our traffic. So when we have many paths, out of many, the path with more bandwidth or the path with enough bandwidth to send my data is what need to be elected. That is what traffic engineering do. Listen carefully, I repeat. This is my house and this is airport. My house. There are 3 roads to the airport, one straight like this, another one like this, another one like this. There are 3 roads to reach airport. This is 25 kilometers. This is 31 kilometers. This is 51 kilometers. Now, if I will run a protocol like OSPF, it is going to pick this path because this has got more bandwidth and less kilometer. Let's say the bandwidth of the road is 100 meter. The bandwidth of this road is 300 meter. The bandwidth of this road is 150 meter wide. Okay. Now, this has got more bandwidth, no doubt, but more kilometer also. So the delay is going to be high here. So OSPF, let us assume OSPF takes only this path. It says, J, you go from here to here using path 1. So everyone will be using that same path 1 from my place to the airport because OSPF says path 1 is the best path. Path 1 is the best path, but so everyone wants to use it. Everyone, which means traffic is going to be very high. As a result, the available bandwidth in the path is going to be less. Even though it has got, okay, let me make it as 200 here. Even though it has got 200 meter wide, this is only 150 meter wide. Even though this has got 200 meter wide, because everyone is using that road, the available bandwidth will be very less. For example, let's say you got only 20 meter left. Only 20 meter. With a 20 meter, definitely one car can go. So let me make it as 10 meter. You got just 10 meter out of 200 meter. You got 10 meters. It's also a big number only. For a car, you can easily go. But let's say you are driving a truck from your place to airport. Just 10 meter wide is not sufficient. So you are bringing a big truck. Big truck. For that, this balance left out 10 meter is not sufficient. Everyone is using this path. Out of 200, 190 is already been consumed by existing traffic. But the routing protocol will keep saying that this is the best path, this is the best path, this is the best path. Because according to routing protocol, it won't see how much load on the path, it will see only how much bandwidth, and accordingly it calculates the cost and gives the best path. So OSPF is not going to change its mind because there is less available bandwidth. See, the total bandwidth on the link is 200. After everyone consuming, only 10 is available. Will OSPF focus on available bandwidth? No, 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 no. OSPF is not going to focus on available bandwidth. OSPF only focuses on what bandwidth the maximum that the interface got. The interface bandwidth only it will take. So routing table always shows path 1. But the truck cannot go in path 1. I need TE now. I need traffic engineer. Because it's a special traffic, it's a truck. I need TE. Meaning I want a path which is not there in the routing table. That's not my aim. I want a path which has got at least 80-meter wide road so that I can take a nice turn. With a big truck, you cannot easily turn if the road is very narrow. You need a wide road. Only then you can make a turn. You are having a big truck. So 20-meter road is not enough for you. In 20-meter road, I cannot even take a U-turn with my small car. How will I take a U-turn with a truck? Not possible. With a bike, you can manage 20-meter road. So this is a big traffic you are bringing. It's a special traffic. It needs special service, meaning it needs a guaranteed bandwidth, available bandwidth on the path to reach airport. For this, if you don't have traffic engineering, this truck will go and get stuck to here. Even for others, it will be a problem. Because the routing table shows only that path, your truck will try to go that path and get blocked. The whole bandwidth will be blocked. Okay, so what is the solution? Traffic engineering, what it does, it looks into the link state routing protocol database. It has got visibility to the other two lines. So it is going to check whether any one of this line has got that 80-meter wide available space. Here I said you got only 10-meter left. So this path will not be approved by RSVP. So this is the job of RSVP. It needs to go and check whether your constraint is met. Your constraint is you want 80-meter wide road. It checks path 1. Path 1 says no. Path 2 says I do have it. That is what called as the reserve message. So the path message will go from here to every single hop asking, do you have 80-meter wide? And this road says, yes, I do. That is what called as reserve message. Meaning, okay, take this path. So when the reserve message comes, the path has been reserved. So a new label, this is the highlight. MPLS working on this router was not having this route in the routing table, so there was no label. Now a new route is being derived by RSVP to provide the service for the truck to go. This road is not in the routing table. You know about MPLS, right? MPLS provides label only for those routes that are there in the routing table. But now RSVP is saying, see, I want a label for this new path. But this new path will not be there in the routing table. I repeat, the new path will not be there in the routing table. RSVP can still provide. Sorry, MPLS can still provide the route recommended by RSVP. For this particular traffic, the road is needed for time being. Once the truck goes to the other side, this road will be closed. So for this temporary, at present, for this truck to go, the road gets open and new label is going to be distributed. So that in this new path, the label switching will happen for the truck as the truck goes to the airport. You see how they are all interconnected. Traffic engineering needs RSVP to check whether enough bandwidth that is needed is available. If it is available, it takes the help from MPLS to provide label. And for RSVP to know the available paths, it depends on link state routing protocol. So they're all interdependent. They're all interlinked. They depend on each other. Then only you get traffic engineering. So now we used to do these things, not we used to, we are still doing these things manually, enabling all this protocol. To avoid our pressure, to reduce our pressure, the automation tools, the controllers does this for us now. The controllers does this for us. Softwares does this for us. But those things came very recently in concepts like SD-WAN and some other software-defined solutions. But behind the screen, this is what it is going to do when you enable such application-driven networking. Without knowing this, just knowing that application is not going to qualify anyone as an engineer. Knowing this is more important than going and using those tools. It consumes a lot of processor, a lot of money. You need to buy the controllers, which is costly. You need to buy the devices, which is again costly to support SD-WAN or any other ACI kind of. You see, so far what I have said is what all it takes for traffic engineering, and also I have indirectly taught you what is traffic engineering. Traffic engineering is choosing a path which will satisfy the requirement. What requirement? Bandwidth requirement. You want so and so bandwidth. For example, you want 80 meg guaranteed bandwidth for my traffic to go. So RSVP will go and check on all the available paths for this 80 meg end to end. End to end, that is very important. From my home to the airport, from the source to the destination. In between, you may have 100 routers or 1000 routers in between. End to end, the bandwidth that you need, 80 meg, needs to be there. That is checked and confirmed using RSVP. Once the confirmation is done, that is called reserve message. Once the reserve message is received, MPLS provides label to that reserved path. Using that label, packets are going to be forwarded. Any question?
Sir, once we get the reserve message, then we will see a different route when we give show
No,
IP route command.
in the routing table you will not see. But when you type
Okay.
show RSVP, something like that, RSVP related commands. When we go to the configuration, I'll say, okay, we have the sample output right here in the document which I shared with you. If you see configuring TE on the interface and the tunnel, let's go down and see some show commands. So show RSVP TE, I think the command is show RSVP. I just want to see some show commands. This is not the page which I, is this the one? No. Ah, show MPLS traffic engineering tunnels. When you put this command, it will show you the elected path. It will show every hop. See, it displays information about the configuration of MPLS TE tunnel at the head end and signal TE label switch path. This is what it shows the path at every hops. It shows the path. So this is the command which will show you what path is currently being used. Yeah.
Okay.
Just don't have enough information. We need to also go to next chapter, chapter 12 of this book. Internals, it will show you whether the tunnel is up, administratively also it is up, and if you go down, you will see the path that it has taken. This is the
Okay.
hops via which the traffic is going. The source is this, the destination is this. You see the destination here. To reach the destination, this is the path via which the tunnel is established. So what is the
Okay.
constraint? The constraint is you should have the path with at least 1000 bytes. That's the condition, constraint based selection. No, they did not say any constraint. They just wanted path. IB interface, this is the destination. Traffic engineering is enabled. Auto reroute is there. Dynamically it is asked. There is no constraint. This is not a real traffic engineering. Real traffic engineering should have a constraint based. We'll do some example with constraints. It's just sample. So I think this document is quite good in previous ones. So what we have seen is traffic engineering is basically the best way of picking the path. Routing protocols provide path, but that may not be best all the time. As we saw one example, when there is heavy load on the path, our traffics may not be comfortable to pass through the path. When there are other paths which are idle, RSVP can wisely use those other paths in order to provide the best service, for which we need traffic engineering. 1 minute.